begin. Hello. Welcome to your first Algebra 1B lesson. This is so weird with only one student. So in Algebra 1B, we only have 2 units. So about half of our time, we're going to focus on Unit 6, since it's the second half of Algebra. Unit 6, which is going to be all about something called a system, which is what we're going to introduce today. And then the second half of Algebra 1B, we're going to focus on quadratics. So to start us off for our unit, we're going to talk about solution points of systems. This will be like a good introduction lesson, so you'll get a feel for what we're going to be looking at in this entire unit. So to begin, we're going to start off with what is a solution point. Our definition for a solution point is going to have 2 parts to it. The first part is that it correctly satisfies the equation. That is like the fancy math way of saying if you substitute in the numbers, it gives you something that's true. So if you think back to when we were checking equations, what it means to check an equation is if you substitute the value into your equation, it gives you something like 5 equals 5 or 10 equals 10. This is what that's saying, is it satisfies the equation. And then the second part is the point lies on the line. So if you think about if you were to graph a line of that equation, any point on that line would be a solution point. So to help this make more sense, we're going to start off with an example of something you saw back in Algebra 1A. So I've got a story problem here that says Flora is saving money. She starts with $30 and saves $5 each week. The equation and graph below represent this. And you've got 2 ways to see it. I've already turned this story into an equation for you. So we've got the $5 each week plus the $30 she's starting off with. And then I've also already graphed it for you. So we've got it starting at $30 and she's saving $5 each week. $5 each week. This came from a problem you did back in Algebra 1A. What we're looking at today is this idea of what a solution point is. So I could give you all of this information and ask you, is the point 450 a solution point? Using that definition of solution points, remind me what a solution point is.
Point that correctly satisfies the equation and lies on the line.
Yeah. So one way we could check to see if a point is a solution point is by checking to see
if it lies on the line.
Yeah. If I wanted to see if 450 is on that line, how would I find the point 450?
You go to 4 on the x-axis and go up to 50.
Yeah. So is that point on the line? Yeah. So one way you can do it is using the graph. The other way you could do it is, read that other part of the definition.
Correctly satisfies the equation?
Yeah. So we could check if we didn't have the graph, or maybe if the numbers are too big for the graph. We've also got this equation we could use. So we could check to see if this point satisfies the equation, which I said earlier is similar to when you're checking an answer in your equation. I'm going to substitute both of these numbers into the equation. Which number am I substituting y for?
The amount of money. So
Oh, yeah.
50.
You're going back to the graph. I like that. I'm going to do this one. I see where you're getting the 150 from, but let's do this one first. So I'll do y as 50, and then x will substitute our 4. If I'm checking to see if it's a solution point using what you're saying, substitution, what's it going to say?
The 50 equals 20.
Ooh, you're already doing the math. So 5 times the 4 gives us 20.
Plus 30.
Is that true?
Yes.
Yeah. So that's another way you can check it. When we're saying 450 is a solution point, you took it back to what those numbers mean already, which I love. When we're saying 450 is a solution point, what we're saying is for 4 weeks, she does have $50. If I'm asking you, is the point 20, 150 a solution point? Put it into words like we just did. What does this point mean?
It'd be 20 days and $150.
You're so close. It would be
Or 20 weeks, I mean.
Yeah.
So
Yeah. So what we're checking is if it's a solution point. But the meaning behind it is, at 20 weeks, does she have $150? Now this one, we pointed out earlier, the numbers are a little bigger. Could I check this point with our graph?
No,
Why not?
because it doesn't extend that far.
Yeah, if I had a larger graph, I could. But that's why we've got all these different ways to represent the story is if the graph is too small, it's okay because we have an equation. So for this one, what would checking it to see if it's a solution point look like?
You would put it into that original y equals 5x plus 30. So it would be 150 equals 5 times 20
Mm-hmm.
plus 30.
Yep. So we're substituting our point into our equation. We get this. So I could say 150 equals
100
nice.
plus 30.
100 plus 30. Is that true?
Mm.
No, because 150 does not equal 130. If that's not true, what does that mean?
Not a solution point.
Yep, it's not a solution point. It also means, if we go back to like what those numbers mean, it means at week 20 she doesn't have $150. She's got some other amount of money. Questions on what a solution point is, how you check to see if something's a solution point? You're feeling okay?
Mm.
Okay. Then I have got, this one for you to try. It should be on the back side of that paper. I'm giving you a different equation. I'm not giving you a graph. But I am asking you, is the 0.23 a solution point? I'll go ahead, give you like 30 seconds. It's just you now, so you let us know when you're ready. You want me to check your paper? What you get?
3 equals 4 minus 1.
Is that true?
Yes.
Is it a solution point?
Yes.
Yes. And there's the graph for it. So now that we've got the graph, we could also see the 0.23 is on the line. When you think about solution points and solution points of a single equation, how many different points could I give you where you would say, yes, that's a solution point?
An infinite amount?
Ooh, look at you breaking out that math word immediately. Yeah, what's infinite mean?
Never ending.
Yep. So we're going to say there are infinitely many solution points. Sometimes when people focus in on the graph, they say, okay, well, I see 1, 2, 3, 4, 5 points on it. So there's maybe 5 solution points. But remember you said earlier, you used that word extend. This graph can extend infinitely, to use that word. You know, this line goes on forever and ever. And then it's also to remember, there's all these like nice points that we like to use when we're graphing, but there's also all those points in between that would have decimal numbers for them. So even on this graph, I can see infinitely many points because between each of those little tiny points is another point. So that's going to be important. If you're talking about a single equation, there are infinitely many solution points. That's no fun. However, the focus of this unit isn't on single equations, it's on something called a system of equations. When you talk about systems of equations, a system is going to mean it's a set of 2 or more equations. In Algebra 1, we keep it to just 2 equations when we talk about systems, but in Algebra 2, you see a lot of problems with 3, I'm holding up 3 fingers, with 3 equations. In college, if you wanted to study math, you sometimes have problems with 4 or 5 equations. It can get, I like that sound, it can get real fun, but for now we're gonna just look at systems with 2 equations. And those 2 equations are gonna have the same variables. I need a new pen. The same variables in them. So for that last problem, we were talking about money and weeks. If I were to write 2 equations, both equations would be talking about money and weeks in them. When you're talking about solution points for a system of equations, the definition is very similar. It's going to say it's going to be a point that lies on since there's two or more equations, it's going to be a point that lies on both of the lines and satisfies
Both.
yes, both equations. So everything we just said for those first two examples will be similar for systems. It's just as true for both. So for example, I could ask you, is the point 2, 0 a solution point to the system of equations? If I wanted to check to see if it was a solution point, what do you think I'm going to do?
Put 2 and 0 into the x, y's.
Mm-hmm. And I heard you say x and y's because we're going to do it for both equations. So if I do that, I'm going to focus in on this first equation here. What would it say when I substitute? I'm going to label it real quick for us.
You could do -2 times 2
Mm-hmm.
plus 0 equals -4.
Love it. And then same as earlier, we're checking to see is that true. What would that give me?
The -4 plus 0 equals -4, which is true.
Which is true. So we've got this point here is a solution point for that equation. You had said earlier we want to check both of them. So we still got to do this one. What's it going to look like when I substitute here?
So it would be 0 equals -3 over 2 times 2 plus
Times 2, yep. Plus 3. Now, to help with that fraction multiplication there, I'm going to actually recommend that we write it like a fraction as well, because when you're multiplying fractions, you're just multiplying straight across like that. So we get 0 equals
-6 over 2.
Mm-hmm. Plus 3. And then -6 over 2.
-3.
Plus 3.
So that's correct.
Yep. So by doing that, we figured out that this point is a solution point for this equation. So is that point a solution point for the system of equations?
Yes.
Yes. What would it have meant if it checked out for one of them but not the other one?
It would not be a solution point for the system of equations.
I like how you phrased that. It wouldn't be a solution point for the system. What would it mean?
It would mean a solution for one of them,
Mm-hmm.
but not both.
Yep. If I went back to the graphs, thinking about the graphs earlier, what would it mean for the graphs if it was a solution point for one but not the other?
You could graph it and it would be true on the first graph, but not on the second one.
And what do you mean it would be true on the first graph?
It would be a solution point
So where would I find it if it's a solution point?
on the line.
Yeah. So what this would mean for the graphs then is that this point, if this one had been a no, it would mean that this point is on this line, but not on this line. We found that it was a solution point for both. So what's it mean about this point on the graph?
It would be on both lines.
Yeah. I'm going back to the graphs just because that's going to be a big theme in tomorrow's lesson is what these graphs look like. And you're already doing great with that. How do you feel about the math, the checking to see if it's a solution point?
I'm good.
Okay. It's like you're like half teaching the class. You've probably never participated so much in a class before. I'm going to have you go ahead and try this one, okay? Denise, should I call on you some just to break it up? Let me come peek at your paper. I love it. And now that you're doing so great, this video is going to be super short. Well, it's long, so it's not like the wire's tight and I'm gonna like trip on it. I just keep stepping on it. I don't know if I'm used to it. I've been like walking like this.
Okay.
So answer the question for me. Is the 0.43 a solution point to the system?
No.
If I asked you to explain why, what would you say?
Because for the first equation,
Mhm.
it is a solution point,
Uh-huh.
but for the second one, it's not.
Right. For that second one, you end up getting, what's the math look like when you check? 8 minus 9
Mm.
equals -1?
On my paper, it says 1.
That would be why. I was like, wait a second. So 8 minus 9 does not equal 1 because it equals -1. If I had given you the problem that's currently on the board, our answer would be
It is a solution point for the system of equation.
yes. It's like I meant to do that. Bonus question. Okay. Like I said earlier, the direction we're going to go in tomorrow is looking more at the graphs of these. So at this point, I just want to pause and talk about what these graphs would look like. So we said earlier, when you're talking about a single equation, we said a single equation has how many solution points?
Infinite.
Yeah, because there's tons of points that lie on a single line. And to be a solution point, it has to be a point that lies on the line. When you're talking about a system of equations, we said a system of equations is?
Multiple equations.
Yeah, so 2 or more equations. For my drawing, I'm going to say 2 equations. If we've got 2 equations, that means 2 lines. And assuming the 2 equations are different equations, it means 2 different lines. We said to be a solution point for a system of equations, what needs to be true?
The
Point?
The point has to be correct for both. So it
Right.
has to be
You
a
got
solution point for both.
Yeah, it's got to be a solution point for both, and it's got to be on both lines.
Yeah.
So in this drawing I did, how many solution points does that system have?
1.
Why only 1?
Because the line only crosses through each other once.
Why isn't this a solution point?
Because it's only on one line.
Yeah, and it has to be on both. And you already nailed it. That solution point is going to be where those lines cross, intersect, however you want to think of it, because that is going to be the only point that's on both lines. So when I said earlier that, oh, it has infinitely many points, that's no fun. With systems of equations, so many of our systems only have 1 solution point. And so a big focus when it comes to systems of equations is finding what that 1 solution point is. This has got an infinite amount of answers. This has only got 1. So a main focus of this unit is going to be finding that 1 solution point. All we've been doing today is saying, yes, it is a solution point. No, it's not a solution point. But starting tomorrow, you're going to actually be finding what that 1 point is. How's that sound?
Good.
The first part of this lesson was on systems of equations. The second part of this is on systems of inequalities. So just like in Algebra 1A, how we learned about equations and then switched it over to inequalities, this unit's going to be similar. You can probably guess a system of inequalities is going to be a set of
Solution point? Or equations. Inequalities.
Yeah, so a set of, we're going to say the same thing as before, 2 or more inequalities. When I say inequality, what am I talking about? Yep. For the camera, he's doing this with his hand. So it's those less than, greater than signs. So a system of inequalities is going to be a set of 2 or more of these with the same
Solution point.
We can say that. The same solution points. I'm also going to say the same variables again. So if one of them is using x and y, the other one also has to use x and y. They're both referring to the same variables. So to be a solution point for a inequality or a system of inequalities, the idea is very similar. Again, I'm going to start off with something you saw back in Algebra 1A and then relate it to what we're talking about with solution points. So I've got Tope makes money selling refrigerators and washing machines. He makes $100 for each washing machine he sells and $200 for each refrigerator he sells. His goal is to make at least $1,600 this week. The graph and inequality below both model this situation. So similar to the first part of this lesson, I've got the inequality that's already written for us. Going back to the word problem, what is this saying? We've got
$100 per washing machine
mm-hmm.
plus $200 per refrigerator
Mm-hmm.
is greater than or equal to 1,600.
Yep. He wants to make at least $1,600, which means he wants to make equal to $1,600 or greater than $1,600. So we've got the inequality already written. I've also already graphed it. Again, this came from a lesson you've already done. And one of the differences with graphing inequalities, you saw on that do now, is we've got this shaded area here. In this problem, do you remember what that shaded area there means?
How much has to be bought for him to reach his goal?
Yep, I'm going to change that a little bit. He's not buying stuff. What is he doing?
Or so much he has to sell.
Yeah. So a point in the shaded area, I'm going to use this one as an example. What does this point here mean?
It means he sold 12 refrigerators
Oop. Yep, 12 refrigerators and
10 washing machines.
and keep going. He sold 12 refrigerators, 10 washing machines, and you'd mentioned earlier his goal. How does it relate to his goal?
So he reached his goal.
Yeah, he made at least $1,600. One more like that. This point here, what's that point mean?
It means he sold 4 washing machines and 2 refrigerators, which means he did not reach his goal.
Yep, 4 washing machines, 2 refrigerators, didn't meet his goal. So over here, we're relating it now to solution points. When I'm asking if the point 6,4 is a solution point, just like you were doing, one way you can check it is by taking that point and finding it on your graph. So the point 6,4, 6 for x, 4 for y. Is it a solution point? No. If I wanted to put words with this, what does the point 6,4 represent?
It means he sold 6 washing machines and 4 refrigerators.
Mm-hmm. And when we're saying it's not a solution point, what does that mean in this situation?
It means he did not reach his goal.
Yep. So just putting words to the math. One way we can do that is with the graph. Something like this. Is the point 40, 0 a solution point? Can we use the graph?
No.
No. If I tried finding 40 on our x-axis, this graph is too small. Does that mean all hope is lost? What could we do?
We could see that since
I see what you're about to tell me.
even if you don't sell any refrigerators, you can sell 16 washing machines and reach your goal, or reach his goal. So if you can get to 16 and you reach your goal, if you get to 40, you also reach the goal.
You're so smart. I'm going to repeat it just in case the microphone didn't pick it up. So what he's saying is he's noticing on this graph is if you sell only 16 washing machines and if you don't sell any refrigerators, that's like the bare minimum you need to sell of just one, and anything more than that's going to be in the shaded area. So he is right. So we could say, is it a solution point?
Yes.
Yes. I'm going to press you further. If I did not have any graph at all, does that mean all hope is lost?
No.
What else could we do?
You can do the math with the inequality.
Yeah, I like how you called it an inequality. So if I take that inequality, what do you mean do the math with the inequality?
And then plug in the points into the x and y.
Yep. If I'm substituting, what's going to go right there for x?
B times 40
Mm-hmm. And then for y?
Times 0.
Times 0. 100 times 40?
4,000?
Nice. 4,000 plus 200 times 0?
0.
Is this true?
Yes.
Tell me why that's true.
Because 4,000 plus 0 is greater than or equal to 1,600.
Yep, 4,000 plus 0 is 4,000. And what you did that I liked is you read the entire statement. I heard you say 4,000 is greater or equal to 1,600. A mistake that students make with this sometimes is they're thinking back to equations. If this was an equation, these numbers have to be the same. It needs to say like 4,000 equals 4,000, 1,600 equals 1,600. But because it's an inequality, we're paying attention to that inequality sign. And you read 4,000 is greater than 1,600. So when you're checking these, if you're using the inequality, make sure you're focusing in on that inequality sign. We're not necessarily looking for them to be the same number. How do you feel about this?
Good.
Okay, so we're going to take away the graph, the story, and just look at the pure inequality, I guess, the system of inequalities here. Similar to what we were just doing, if I asked you, is the point -4, -5 a solution point for the system of inequalities? Something that's different this time is it's now a system, but the idea is going to be the same. If I want to check to see if this is a solution point, what you want us to do?
Put the -4, -5 into the x and y's.
Yep. So if I do that for this first inequality, what is it going to say?
Say -x times -4
-x times -4.
plus -5, or no, so it would just be -5
You can say plus -5, but I agree. It's easier just to say -5.
is less than 2.
Pause there real quick for me. You told me what were we going to do with these numbers?
Carry them to x and y.
Replace x and y with them, substitute x and y with them. If we're substituting, if we're replacing, that means there shouldn't be any x and y in our work.
Oh yeah. So there's no negative x. It's just negative x into -4. Be positive 4.
Nice, yeah. So I don't want that x there, but I do want that negative because I heard you say -4 would be +4. That negative sign there can trick students sometimes. So we've got 4 minus 5 is less than 2.
Yes.
Yes. Why is that true?
Because 4 minus 5 would be -1.
Nice.
And -1 is smaller than 2.
Yeah. Are we done?
No,
What do you want to do now?
the second one.
Okay.
Second inequality.
Mm-hmm.
So that would be -4 is less than
Mm-hmm.
-2 times, or wait, no, that's the so it's -5 instead of
There you go.
-4.
Yep. I like labeling them. I just think it helps make sure stuff goes in the right order or in the right spot. So we changed that to our -5, and then you caught it over here. It should say -2
Times -4
Mm-hmm.
minus 13.
Yep.
And then -2 times -4 is +8
We get -5 is less than 8.
minus 13. And then 8 minus 13 is -5.
Uh-huh. What do you think about that?
So it would not be true.
Why is that not true?
Because it just says less than, not less than or equal to.
Good. So it just says, and I was about to ask you that question, but you already answered it because it says less than and not less than or equal to. If it said less than or equal to, then it would be true. So it says this, so you said that's no good. So to answer the question, is the point a solution point?
No.
No. How are you feeling about these? Excellent. I've got this one last one here for you. Do you want to do it on the board?
I guess.
Your face looked like a no. You don't have to if you want. If you don't want
Might
to.
as well.
Okay. There you go. All right. Talk us through real quick. You don't have to explain all the math you did, but just say why you, yeah.
So this one says -6 is greater than or equal to -5 minus 1, which would be -6. So this is true.
It's true because
-6 is greater than or equal to -6.
perfect.
And then with this one, -8 is less than -7, which is true.
Now, why is that true? Because I see an 8 and a 7.
Wait, no, it's not true.
No, just tell me what you're thinking.
Or, well, I was thinking because, like, whatever is on this side of the inequality is the larger number.
So is -7 larger than -8?
Yes, so it is true.
Why? Why is -7 larger?
Because -7 is closer to 0 than -8.
Nice. So that's one way you can think of it. When they're both negative, it's so easy to get that confused right there. I had you convinced you got it wrong when you were right. You can think of it that way. So it sounds like you're kind of picturing a number line and which one's closer to 0. You can think of it with like temperature or money. Like -8 degrees is colder. It's a lower temperature. With money, -$8 means you owe $8. That's less money than you owing $7. Lots of different ways. But you ended up saying, yes, it's a solution point for the system of inequalities. Yay! That is everything for today. I'm exhausted. Are you exhausted? You must be. That was a very involved lesson for you. Do you have any questions for this?
No.
All right. Hopefully you're feeling great at home. Goodbye.